Lesson 34, demo. In this class, we use L'Hopital's rule to evaluate certain kinds of limits. First, a brief history lesson about, okay, so this guy I'm just going to call L'Hopital. My French is not good enough to say his entire name, but this whole thing is his entire name. Lived late 17th century. He was a French mathematician who wrote the first European textbook on calculus, but the quotes are necessary because virtually the entire textbook was lifted directly from notes made by Johann Bernoulli. L'Hopital paid Bernoulli to tutor him in calculus. Bernoulli was one of only a handful of people in the world who understood this newly discovered subject. In order to tutor L'Hopital, Bernoulli, they didn't live near each other, so Bernoulli just wrote a bunch of notes on calculus and mailed them to L'Hopital. L'Hopital promptly took those notes, slapped on a cover page with L'Hopital's name on them, and published the book as his own. We only learned this after the fact. Bernoulli didn't say anything about this while L'Hopital was still living, although Bernoulli was obviously very upset by this deception. But he felt that because L'Hopital had paid him, that Bernoulli didn't have a right to come up and say, hey, that's my book. He felt like he was paid for his services, but he wasn't happy about it. L'Hopital passed away. At that point, Bernoulli felt free to share with the world, hey, this is actually mine, it's not L'Hopital's. But this rule that we now call L'Hopital's rule, the name was already given by that point, and it was just too late to change it. So we are stuck with L'Hopital's rule as a name, although technically, really, it should be Bernoulli's rule. Okay, full disclosure, we aren't going to be making heavy use of L'Hopital's rule in Calc 1 or 2, but it will be on the next test and the final exam. Let's find the following limits. First one is the limit as x approaches 1 of all this stuff. The very first thing we should do with every new limit we encounter is simply plug in 1 for all of the x's in this case. Okay, so upstairs 1 and 2 is 3, minus 6 is negative 3. Downstairs 7 minus 4 is 3, plus another 3 is 6, negative 1/2. Done. That is the answer. No need for any fancy tricks, any fancy limit stuff, or even a fancy L'Hopital's rule. Again, the point of this is to remind you that the first thing you should do when you have a new limit is to just plug in and hope you get something nice, just like a normal number. Okay, but things are not going to work out as nicely here in B. Let's see what happens when we just plug in. So we're going to plug in 2 for all of these x's. I don't really have room there, so I'm going to do it over here. So 3 times 2 squared minus 2 minus 10 over, and then 2 is down here for all the x's. Okay, upstairs, 3 times 4 is 12, minus 2 minus 10, and then downstairs 5 times 4 is 20, plus 6 minus 26. And upstairs we get 0, no problem. Downstairs we get 0, yikes. So 0 over 0 means that there's more work for us to do. And early in this semester, very early in this semester, we talked about limits. And the technique that we used for problems like this was to factor. Remember, we called 0 over 0 an indeterminate form, which meant that the limit could actually be anything. And so we had to do more work to find out what it was. So we haven't actually calculated the limit, so we got to write this again. And now we're going to factor. And both of these trinomials are going to factor into the product of 2 binomials. But these ones are tough for me anyway. I'm much better if the number in front of x squared is a 1. So I guess there's only one way to make a 3x squared. That's going to be a 3x and an x. And I'm trying to make a minus 10. So I'll put over here. I don't quite know what it's supposed to be yet. So I don't know. Is it a minus 10 and a minus 1? I should not have used the magic pen for this. Okay, so is it a minus 10 and a minus and a plus 1? Maybe something like that. And so if we check our outers and inners, that's a positive 3x and a negative 10x, and that's a negative 7x, which is not what I wanted. Well, shoot, that didn't work. So maybe it was supposed to be a minus 1 and a plus 10. I need to stop using the magic pen. So maybe it was supposed to be a minus 1 and a plus 10. And then if we do outers and inners, that's a 30x. That doesn't sound promising. Minus 1x is 29x, which is not the negative x we wanted. So it feels like it's not going to be 10 and 1. So the only other possibility is 5 and 2. So I don't know, how about like a 2 here and a 5 here? So what do we get? That's 15x minus 2x is 13x. Nope, not that one. Maybe we swap the 5 and 2. Minus 5 here, plus 2 there. 6x minus 5x, that's positive 1x. Oh, that's really close, because if it's the right number but the wrong sign, we just have to change both of the signs. So instead of a minus and a plus, we should have done the other way. So plus 5, let's do this in black, plus 5. I said, let's do this in black. Plus 5, minus 2, and then we check outers, negative 6x, inners, positive 5x. That's a negative x. That's exactly right. Okay, and so yeah, it's true. I didn't get to the right answer until the last possible option here in terms of our trial and error. And yeah, it's true. I actually did that on purpose, but I want to convince you that it can be really annoying to factor. And this L'Hopital's rule technique that we're about to do is really straightforward. And so I did this one because I wanted to show you that the alternative from earlier in this semester can sometimes be quite annoying. Okay, let's factor the bottom, which is also annoying. 5x here, x here. 26 doesn't have that many factors. Let's see, so it's either going to be 13 and 2. I think that's it. So 13 and 2, and we need the signs right, so it's got to be a plus there and a minus there. And if you check the outers and inners, negative 10x plus 13x is exactly 3x. So we got that one right on the first try. That's because I'm pretty good at this, but it's annoying when you go through the trial and error. Okay, so what do we do now? Well, now we're looking for common factors. And hey, x minus 2 is a common factor, and so they go away. And so that means that our limit is really just 3x plus 5 over 5x plus 13, and that is a brand new limit for us. And when you see a new limit, you just plug in. And so we're going to plug in 2 for all of the x's. 3 times 2 plus 5 over 5 times 2 plus 13. Notice we did not write the limit there because this is the step where we were plugging in. 6 plus 5 is 11. 10 plus 13 is 23. All right, there you go. So this 0 over 0 indeterminate form actually approaches 11 over 23. Okay, so what's the alternative? The alternative is this thing called L'Hopital's rule. First thing you need to do when you before you do L'Hopital's rule is actually try to just plug in. And when you just plug in this case, you get 0 over 0. But you need to make sure that you get one of our indeterminate forms. At the moment, 0 over 0 is the only one, but there are some others that we're going to see today. Okay, so what can you do if you get 0 over 0? So you can do this really wacky thing here. Copy the limit as x approaches 2. And we're going to take a derivative of the top and the bottom of this fraction. Now, I'm not taking the derivative of the whole thing, which would involve the quotient rule. I'm taking the derivative of the top and the bottom separately. It's a really strange thing. Derivative of the top, easy, 6x minus 1. Derivative of the bottom, easy, 10x plus 3. Now, before we continue, I just want to point out again how strange that is, what we just did. Some folks call this the freshman dream. Instead of having to do a quotient rule, wouldn't it be amazing if we could just take derivatives of quotients like this, take the derivative of top and bottom separately? So it simply doesn't work. We saw that earlier this semester. But for L'Hopital's rule, turns out that you can just take derivative of top and bottom and something magical happens. This is a brand new limit, and when you see a brand new limit, you simply plug in 2 for all the x's. 12 minus 1 is 11. 20 plus 3 is 23. 11 over 23 is the answer using L'Hopital's rule. Oh my goodness. 11 over 23 was the answer, doing all of that annoying and possibly time-consuming factoring. And we didn't have to do any of that. We had to do 2 simple derivatives of a couple of polynomials. Okay, so that is L'Hopital's rule. It looks like magic. It is magic, but it works. I'm going to ask you to do something non-standard. I'm going to ask you to put right here on top of that equal sign an LH, and that is your way of telling me that you are applying L'Hopital's rule. You have found that you got an indeterminate form like 0 over 0, and then you are applying L'Hopital's rule. And just note, anytime you apply L'Hopital's rule, when you write for me this LH on top of an equal sign, the very next thing you're going to write is a limit. Very next thing. Have to write that limit because you still need to do the limit calculation after you've done your separate derivatives. Okay, let's take a look at C. Here is the same fraction, but this time we're taking a limit as x approaches infinity. Now, we had a theorem we saw earlier this semester. It was actually a theorem you probably saw in your pre-calc class, which talked about horizontal asymptotes, which is exactly what this is referencing. X going to infinity on a graph says what's happening to the far right, what's happening to the y values, the function values. And we have an easy theorem that talks about how you can find horizontal asymptote for a polynomial on top of a polynomial. All we have to do is look at the we just look at the degree, which is the highest power on top and bottom separately. And if the degree on top is bigger, then there's no horizontal asymptote. And if the degree on the bottom is bigger, then it's the x-axis, which is the horizontal asymptote. But if the degree is a tie, then the asymptote is just the quotient of leading coefficients. So for sure, the answer to this limit is 3/5. And that's almost immediate once you've practiced with that theorem a little bit. Now, L'Hopital's rule is not going to be better than what we just did. Nothing is going to be better than what we just did. But the fact is, that theorem maybe was presented in a hand-wavy fashion. At least that's how I presented it in this class this semester. I just stated it. I said, it's reasonable. It seems to work, so we're going to use it. But let's pretend that we don't have that. We're going to not wave our hands on that one. We're just going to do this one really the way that we should do it, which is not using that theorem, but rather by dividing top and bottom by the right thing. And the right thing in this case is x to the highest power we see anywhere. And in this case, I see an x squared on top and an x squared on the bottom, and it's a tie, so it doesn't matter which one we write. We're making them both x squareds. If it weren't a tie, you would, again, divide by the highest power of x anywhere, top or bottom. Okay, so that is equal to the limit as x goes to infinity. We're going to take that x squared and divide it into all three of the things upstairs. So it's really 3x squared over x squared minus x over x squared minus 10 over x squared divided by, and that was so much fun, we'll do the same thing on the bottom. Okay, and now we've got 6 different terms here. And something kind of cool happens. Oh, actually, I have to simplify a little more first. Equals limit x goes to infinity. Okay, so we're going to simplify each of those 6 fractions. So 3x squared over x squared is just 3, minus x over x squared is 1 over x, and then I'm copying the minus 10 over x squared, all divided by 5 plus 3 over x minus 26 over x squared. Okay, now something magical happens, because x is approaching infinity, and so this thing right here is really 1 divided by something massive, and 1 divided by something massive approaches a very nice number. It approaches 0. And then 10 over x squared, forget about the minus, but 10 over x squared, when x is massive, 10 over a massive thing squared is also approaching infinity, even faster than the 1 over x. Sorry, it's also approaching 0. And is approaching 0 faster than the 1 over x. And then this 3 over x, 3 over something big approaches 0, 26 over something big squared approaches 0. And so when all is said and done, the only things that are still left are the things that had no x's in them, and that's a 3 on the top and a 5 on the bottom. Don't need to write the limit anymore. We've already taken it. Okay, so really that's what we should be doing instead of using this little shortcut theorem up here. So we're pretending we don't have the shortcut theorem, and that at the moment, this divide everything by the highest power you see, and then do lots of fraction separating, and then fraction simplifying, and then lots of things going to 0 until you finally get the answer. Let's pretend that's our only option right now for calculating this limit. So here's a better option. We're going to apply L'Hopital's rule. But before we apply L'Hopital's rule, remember you have to try plugging in. And when I plug in infinity on the top, well, I get some kind of difficult calculations. I got 3 times something big squared minus something big minus 10. Okay, relative to the infinity, the really big thing I'm plugging in for x is the minus 10 is negligible, right? It's a drop in the bucket. So I'm going to ignore that thing. And it seems like 3 times infinity squared minus infinity would seem like this minus infinity is significant, right? Subtracting infinity feels like a big deal. But relative to the squaring of that massive number, actually subtracting the massive number itself, the minus infinity, is also negligible. Infinity squared, the x squared dominates the x eventually. And so I'm actually going to also ignore that. And likewise, on the bottom, the minus 26 is negligible and the 3x is negligible, only because x is going to infinity. If x was going to some finite number, what I just did where I ignored some terms, that's going to lead me to the wrong answer. But because x is going to infinity, all that matters is the leading term on top and the leading term on the bottom. And so if I send x to infinity, then the top is 3 times infinity squared. Well, that's clearly infinity. And the bottom is 5 times infinity squared, which is also infinity. And so I will say that our indeterminate form earlier today was 0 over 0. And earlier this semester, that was our only indeterminate form. But now we have a brand new one. Infinity over infinity is also an indeterminate form. And for any indeterminate form, 0 over 0 or infinity over infinity, we are allowed to use L'Hopital's rule. Equals fancy LH. Always after those symbols, you got to put your limit. And now we'll do our freshman dream, where we just take derivatives of top and bottom completely separately, not the quotient rule. 6x minus 1 over 10x plus 3. Okay, and then we're going to see what happens when we send x to infinity, because after all, this is a brand new limit. So x is getting really big, the minus 1 is negligible, the plus 3 is negligible. And so that means that the top and the bottom are 6 times infinity and 10 times infinity. They're both going to infinity. And so again, we get infinity over infinity. And if you get infinity over infinity, you are welcome to do L'Hopital's rule. And so it's perfectly fine to do L'Hopital's rule more than once in a problem, provided you continue to get indeterminate forms. So taking a derivative of the top, that's just 6, and of the bottom, that's just 10. And now that it's just 6 and 10, sending x to infinity makes no difference because there's no x's left over. So our limit here is simply 6 over 10, which reduces to the answer we were expecting, 3/5. So I know that there's no way to make this problem shorter than to just say, oh, it's a tie because of the x squareds, and so the answer is the quotient of 3 and 5. But if that is not one of our possible techniques, then your only two options are the stuff we did in blue and the stuff we did in black. Which one is better? Sure feels to me like the black is better. Okay, here are some basic limits that will prove useful in the activities and the homework. If you have 0 divided by any number other than 0, that's just plain 0. If you have any finite number over infinity or minus infinity, that limit approaches 0. If you have any finite number over 0, if we have like a limit, like this isn't really quite 0, but it's heading to 0, then that limit approaches either positive infinity or negative infinity. You got to check the signs of numerator and denominator to decide the sign of the final answer. For example, if this finite number on the top was a positive and the thing on the bottom heading to 0 was heading there, but it was always negative, heading to 0 but negative, then the quotient would be a plus divided by a minus, which would head to minus infinity. Okay, if you have plus or minus infinity over any finite number, that heads to either plus or minus infinity, but you don't get to just copy the symbol from there. You got to make sure you check your signs again. Okay, and then the above technique, the L'Hopital's rule technique, works for general limits of indeterminate form of type 0 over 0 or plus or minus infinity over plus or minus infinity. That is to say, any combination of infinity on top and infinity on the bottom is fair game for L'Hopital's rule. For example, if the top is negative infinity and the bottom is positive infinity, that's fine. Any combination of those signs. This technique is called L'Hopital's rule. It's written out there. It just says that you get to do the freshman dream, that the limit of f over g is really the same as the limit of f prime over g prime. Okay, so I think that's the end of the demo. We're not going to actually prove L'Hopital's rule. I think there's a proof in the book. Certainly you can find proofs online, but we will use it. It works.